Without a problem that I can't fix, 'cause I can do it in the mix. Without a
Just a second, I got lost. I'll just drag it to the other desktop. Okay, please remember that we will be using Cody this year to cast your votes for the talks. So you have to go for registration at the URL at the top. If you remove live, the word live, you will get in directly and you will input your phone number. You'll get a text message. If you use the code you get, and then you input root 17, ROOT 17, that's the code in capital letters. With both things, you register and you will have a balance so that you will be able to transfer money or the balance of your phone account to the speakers. So the volume of the sphere represents a larger amount. Someone as good looking as me, well, I got 5.29 euros, which is not bad. Don't get overexcited and pay €1 to any speaker, even if you like their presentation. And remember to redeem the coupon, otherwise this will go against your actual balance in your phone number. So use the coupon and redeem it so that you can transfer against it. Allow me to go back. Just a sec. So there we are. This is the registration process. Remember the coupon, redeem it, ROOT 17. We would also like to thank our collaborators. They help us every year. Obviously our volunteers. That's Valeria, after her efforts. Now I'll remove the connection. One last thing on housekeeping, very important. I told Abel that he had to be here today because he was elected as the best speaker in 2016. So congratulations, Abel, and thank you very much for being here. Thank you. We'll give you everything formally later on. Abel Valero, well, he'll introduce himself. Good morning, everyone. Thank you for waking up so early to be here. Thank you to Rooted for inviting me along one more year. I had no idea. I was acknowledged as the best speaker last year. Anyway. I'm not sure the audio will work. I'll talk about Radare2 and tell you about malware analysis, which is what I do every day. What you see here is the summary of the 10 years of life of Radare. The different collaborators. A nice animation to show you graphically what has been going on. This will be an intense presentation, so I'll move on. Abel Valero is my name. These are my contact details on my Twitter account. I'm a CTF player with the Amnesia team, the good ones, by the way. Because a journalist chose our logo and decided to say that we were the guys behind hacking a number of websites, but that's not us. We're the good ones. I'm a collaborator with Project R2. I've been there for 2-3 years already. I'm a member of the email list for malware. There's a very large community out there. We rely on each other. I'm working currently, and I've been there for more than a year, analyzing malware for Panda Labs. So, Radare2, what is it? This is a framework for doing for reverse engineering. We have the console, but we also have user interfaces. In theory, you should use the console to do your commands and get responses. Radare2 is an evolution of the previous version, as you can imagine, created by Sergey Alvarez, Pancake, who used an hexadecimal editor to recover files. So we added a debugger, we added binary analysis to make it become what it is today, a program that can be used in many different environments for binary analysis. It is completely open source. It is multi-platform. It has been ported to Android, to GNU Linux, to BSD, iOS, basically anything you can think of. It is multi-architecture. It supports WebASM, 6502, 8051, well, all those things you see in that list. Supported formats. It supports BIOS, CGC, DEX, ELF, well, lots of them. It can interpret them and it can show them. It's got a multitude of bindings that allows us to interact with it with our favorite language, whatever it is, Python, .NET, anything you may like, Ruby. The recommended way to use Radare2 in any project is through R2 pipe. R2 pipe is an API that allows you to tell Radare to execute any of its commands, giving you an output that you can process as part of your programs. I'll tell you a little bit about Radare's community. Quite an active community, actually, with around 300 people. We have an IRC channel where we have as many people as in the community. These two things are synchronized through a bot. If you use Telegram, you will be able to see everyone, talk to them, mention problems, raise doubts, whatever. you will be able to find people like Pancake, Meijin, Alvaro Felipe, all of them very active in the project and always responding to any doubts or questions. And together with them, there's more than 500 people that are always willing to lend a hand. Radare2 turned 10 years old relatively recently. The project is older as Radare, but Radare2 turned 10 years old. This is the gift given to Pancake in an event that was hosted in Barcelona. Some 120 people attended from at least 6 different countries, all using Radare2. So there were workshops, courses on exploiting, on AVR, on different types of projects. There was a command that can find problems in memory. Well, quite an interesting event, a very comprehensive one. This is something that we're hoping to celebrate every year. So who uses R2? Radare2 is being used by many CTF teams, like the guys in the Intrepids team, Dragon Sector, Insanity, they're here in the room as well, and obviously my own group. Researchers from different fields, Sergi Alvarez, he's the author of the Beast. They use it quite thoroughly in his company. We also have Oleandre Vatlaravnas, he's the author of Frida, a library. Frida and Radare have a lot of synergies. There are plugins from Radare to use Frida. It allows us to go into iOS, into applications anywhere. Anything you can think of, through Frida, you can make it work. Both Sergi and Ole work at a very well-known company, ENG Hacking. They use this tool daily. It is actually the only tool they use there for analysis. Alexander Bolshev, also known as Dark Key, well, he's Russian. He's given several talks in Black Hat, talking about Radare, amongst other things. He joined the party in Barcelona, and he showed us the AVR exploit live. He told us about many secrets on how to use Radare for that. Alejandro Hernandez, Nitro USMX, he has written a number of articles on how to use Radare for different things. He gave us training on in Black Hat 2012, off the top of my head. Pau Oliva as well. He loves getting his hands dirty on games like Street Fighter. So he's doing reverse engineering in emulators, amongst other things. Both work, all of these guys work at a very well-known company as well. Then we have Maxime Morin, also known as Meijin. He can be found at the Radare channel. He uses the tool every day for incident analysis. And then we have Jaime Peñalba, I think you all know him, who uses the tool as well. Radare2 was quite a surprise to all users in the channel when we saw that it was featured in Mr. Robot. We had no idea. We saw something like this. There's always a recommendation to use R2 from Git before compiling. In the second chapter, season 2, we could see this snapshot. In this snapshot, in theory, they're modifying firmware. The people that got informed got the right information because the commands are properly used. You can see how they start Radare2, going to a certain position with that command, and then telling it that they want to open a file in write mode. The command is completely correct to go where they want, and then they do a PD16, telling it to show a list of things that you see here. Then it goes to another position on this line. It disassembles that line. It's this one. And finally, it writes on that line. Instead of 74, we have 75. Well, basically no users of Radare would have used that command, but anyway, because they have that command. Radare is a tool that uh, allows people that don't know too much about the architecture to work in different environments. That you need to know about this to change from JE to JNON-E. But we have a command wow swap CJMP, which is very short and very clear. If you're in that position, it will change that instruction and replace it with the opposite. If it's JE, it's JNON-E, and vice versa. Just to show you that Radare has many commands. It can be used in a basic way, as you can see in this example, which is completely correct. And then you have more complex commands, which are very helpful. It may sound a bit overwhelming. Here it is just telling it to write into a certain position with a conditional jump. Okay? If we try to speak in English, well, they all make sense one way or another. Here I have some links. If you're interested, well, you've got the GitHub for the project, the website, the main website, the Twitter profile, the IRC channel in Freenode, and Telegram. If you want to add yourselves to the channel, that's it. The shortened URL and the QR code. You can go into the channel directly by using it. So let's talk now about R2 pipe. The API, which I said can help you move around and be in control of Radare from an external program. Radare is a very user-friendly tool, very flexible. I know you've heard those words a million times, but this is real. The problem with Radare is that when you see a training by Pancake, Pancake starts writing 200 commands on one line, and everything works. A user starting with Radare cannot expect to go that all out right from day one. In this talk, I'll show you, I think, 13 commands. With 13 commands and what I will mention about R2 pipe, we should be able to put together a tool or use a tool in a way that makes malware analysis more agile, faster. So the simpler way to use Radare in our scripts is through R2 pipe. We could use it from Python, install the R2 pipe library. Just say pip install R2 pipe. That's it. It gets installed, and we can start working right away. R2 pipe supports many other languages. Node.js, npm install R2 pipe, that's the command you would need. Vala, Python, Lua, Go, Perl, PHP 5, Ruby, well, you name it, you can work with R2 pipe. This is a script that R2 pipe has been using. Take a look at the import from the library, then there is a command saying open. You tell it what file you're interested in, and then you have the cmd command and the cmdj command. The cmd command will give you an output of what you would see on the screen for the Radare console if we executed a command. Here I'm telling it to show me 3 lines, okay? This would show me the disassembly lines that we saw before, with the bytes indicating the instruction, with the references, whatever. Then we have the option to do CMDJ. CMDJ gives us a parsed output as part of an out.json string. JSON? Out.json? Right. JSON strings are very easy to access. It is easier to work from our languages using JSON strings because we can interpret them quickly, rather than using a gross output that we would need to parse manually. This example you see here does that. It launches a command, gets the output, and then launches another command in out.json, and then prints them both. Not too many secrets. I'll show you a video. I'm not going to load a virtual machine. So I'll show you in a video clip. I'm showing you the pip install. Nothing secret about it, nothing complicated here. So it gets installed. We go to the Radare folder. This was done using a very old version of Radare, but it works. So I'm showing you the script, which is what you just saw. Just copy con to create the file, and after executing, you see the result. We have the 3 lines of disassembly that we're interested in, and then we have the JSON representation of that disassembly. It shows us where the address is for that function, the family, the bytes. So we've got that information is part of JSON. This is inside JSON. Cop is inside JSON. We've got everything. From then on, we can parse and work with it. I'll show you several commands for Radare2 because I'm taking for granted that there's people in this room that have never touched this framework. So if you have no previous knowledge of this tool, we can still try and do some things. In fact, when my talk is over, I'd like to think that you will be able to do some basic things. First of all, Radare has several ways to be invoked. It can be invoked using the command line. If we just say Radare2 space file name, it will open the file in read mode. We will not be able to write on it, but we will have the possibility to see it, launch queries, and do whatever we want with our binary file. We also have the option of using Radare2 with the -d option. Here we open the file in debugging mode. It will open it for the current architecture. Don't go for an ELF file within Windows, because you cannot do debugging. To do that, you have to be in the same platform where you want to do the debugging. In that way, you just debug the file with interruption points. You can move on to disassembly, you can do trace. So anything you can do with any debugger. With the -w option, well, this is exactly the same as Radare2 file name, but it opens it in write mode. If we do changes, if we apply changes to the file, they will be written to the binary image. So changes will be saved. And finally, well, there's many more commands like this. We have Radare2 -n. What this does is initialize the file so that the header is not read. It will open it in raw mode. No analysis will be performed, nothing will be done. No entry points, nothing. Just read mode, skip header analysis. There's quite a few parameters, but these ones are enough to start working with most analysis and run our own scripts. Okay? So, basic commands for Radare. The first one, AAA. What this does, once we have opened the file, is to perform an analysis of the functions in the file to find cross-references, to find parameters that are sent to it, so all the information. Whatever we will need in order to continue with our analysis. If we use that command, Radare2 opens a binary file, but doesn't do a deep analysis, so to say. Okay, this is just basic. So this is an analysis that will show everything you see here. We then have the second command, AXT or AXTJ, the JSON version. With this command, we can go to a function and tell the function, give me all the calls to this function. Okay, those will be the cross references. So I will go into a function like printf and ask it to tell me about the points in the code where there are calls to that function. Then we have the AO or AOJ, again, the JSON version. With AO, we will be at a certain instruction. It will give us data on that instruction. It will tell us about the parameters. It will tell us about the binary bytes that are included. So certain information that we might need to run our scripts in order to simply find out whether the instruction in the disassembly is pushing or something. Using JSON data, we will be able to know whether the instruction equals a push or something like that. Just to give you an example. AFL or AFLJ will show us a list of all functions that the analysis has found. It would be a full list of all the functions that can be found during that analysis. By combining these two commands, we could have a full list of all the functions and then the references that are made to those functions. That in a script, that would be 3 lines of code, no more than that. Then we have the S command. With the S command, we tell it that we want to go to a certain binary, at a certain position in the binary. When we open a binary file in Windows, it usually positions in the address for the header. This is seek to offset automatically at a certain address. Then we have a very interesting command, which is SO. SO is a seek command. But if we do an SO, it will move to the next instruction. The interesting thing about this command is to use it with negative values, because we might be interested, we might be at a certain point, but we might want to see previous instructions to capture data, to do anything. We could do SO -1, and it will go back in the program. SO -5 would go back 5 positions. As you see, these commands are not complicated, and they give us a lot of information for analysis. We have 1, 2, 3, 4, 5, 6 commands. Let's move on to visualization commands. Oh, by the way, I wanted to mention something else. If you take a look at this, in the headers, I have print, debug, basic commands. This is part of a group. If you take a look at Radare commands, they always start with a letter. In the case of P, we have everything that has to do with showing information, with printing data, or with visualizing information of any sort. Debugging commands start with a D. A command may have an output through JSON, and it will always have a J. This is a basic rule that Pancake has established for commands. They're always part of a group that starts with the same letter, and if they are through JSON, they will end up in a J. Anything with a P will be printing, and if it finishes with a J, you will have to do a JSON version. PD, PDJ, this is a simple instruction. We have the PX command. It shows a hex dump. It shows the binary bytes and then shows the ASCII equivalent. P8 or P8J, the JSON version, will show us a hexadecimal dump, but only the values, the bytes. Just imagine that we say P8 for a certain address. The output will be a string EBCE if we're pointing at that address. It will give us the hexadecimal values, okay? Just 9090 EBFE. I don't know, 01, 90, 74, the hexadecimal values only. If we then use it in Python, it would be enough to do a string decodex, or we will be able to decode that information or code it to send it back to Radare. Debugging commands include the typical options. DS, which is debug step. This is step into. This would execute the instruction. If it is a function, we will go inside of that function. It will do debug steps inside. DSO is step over. If I find the function, there will be a breakpoint for the output of that function in order to avoid going inside. If we get an instruction, a loop instruction, is the same story. If we do a DS, it would do it once. If we do a DSO, it would run all the cycles. With DB, we can manage breakpoints. We can introduce breakpoints, get rid of breakpoints. We can go for conditionals. Using these commands, we can always add the question mark at the end. That way, Radare2 will show us a semi-interactive type of help for that command. DC is continue execution. And the DR command will allow us to handle the registries. assign specific values or send queries at any point. Then we have write commands. They start with a W, only one here. Okay, WX, which writes hexadecimal values at the current offset, wherever we are.
En operación.
All right, now I'm looking at time and doing very bad with time. I wanted to show you a demo of basic commands. However, I just don't have the time for it. So very quickly, I'll show you these commands. So you have the output that says channeled. So it has obtained more information, FFT AFL. So here we have a list of functions. It should show us the functions. So you've seen that I've included that symbol, and I'm asking it to show me all the functions that contain the word printf. I'm going now to ask it to give me the references for that function, and it tells me that from this offset, the name of it is printf. So the commands are giving me back the information that I need. So now I'll go to position 4015-4. As you can see, the cursor of radar has changed to 4015E4. So this is information of this instruction. So the size of the code, etc. PD for disassembly. I asked it to disassemble 3 instructions. PD is not represented in JSON. SO-1, I asked it to go back 1 instruction. And now I'm asking it to do the assembly in the point where I am. So we are 1 instruction behind. The analysis has been satisfactory. And it has found previous instructions. Well, the next ones are, the following ones are easier to find than the previous one. PX, this is the output. We see the bytes, representation of them. And here this is represented in characters, P8 character commands that I mentioned before, exactly the same information, but raw information with PJ8. We get the information for those bytes. So demo with debugging commands now. So I guess that debugging commands are not very important for what we will be doing. So here you can see that we have uploaded Radare with -d command to go into debugging. I'm asking it to establish the point of interaction in the program. So I'm asking it to continue up until that breakpoint is reached. I'm asking it to disassemble all these instructions. So now we are on a debugging mode. So we should be here on this instruction now. We'll disassemble the first line. So my cursor is right here. I will do now longer disassembly for you to see DSO, steps over functions. This is not applicable this time. And we can see the cursor here. We have done a BEC here. And well, this is just for you to see the output of the commands that we have run. And now, practical case to use Radar for our in our real life. This is a real case happened to me at work. A colleague told me that an alert has been triggered and that they have found modified DLLs in a file. So they gave me this information. They gave me information about that machine, and I started to do trace analysis. Well, my company, we have a console where we can have the traces of the machine that we supervise, and I can see the processes that have been run on the machine and the execution of the run tree. And I noticed that when those files are created or modified, there is a binary that was in charge of that task. Therefore, I have that binary and I start my analysis. In my initial analysis, I can see that that binary is packaged. So malware creators want to pass a notice for antiviruses, so they do not introduce aggressive code doing very strange things. They have the code to do strange things, but first of all they package it, and this is what the virtual machine will see. So that packaging algorithm that they use make it look very much like legit code, the code that you will find in any program. They try to pass unnoticed so that they are not detected at this point, but they are often detected. So when I unpack the code, I carry out an initial analysis, so there is no reference to text strains. So, but I didn't find any of these. So I don't see any of these, doesn't tell me where it is stored. Therefore, without, well, I guess I'm sure that it's using a wrapper in charge of using the text strain to be used by the code so that it is entered into stack and therefore later on used. Therefore, I do debugging and I can see a number of functions that are decrypting the text that the malware will use later on. So they do it later on so that they do not stay in the memory. So if someone were to do a sandbox, so you will not see any references for any text strains. So a very interesting strain that I found when I do the analysis was server. Server is ransomware. So it hijacks our files. And these people are very nice. They say, well, the worst has already occurred. So your data are encrypted. Welcome to the server community. So they tell you that the worst is over, and now the only thing you have to do is to pay your ransom. And actually, they show it to you in a visual script, and they inform you with a voice of a female. And well, that's it. That's what they do it, how they do it. So the code is packaged by their own packer, and that it changes according to the campaign. And actually, this campaign is very recent. It's less than 2 weeks old. And this, the packaging of this one was completely different to other ones that I analyzed a few months ago. All the chain strains used by this ransomware are encrypted. This ransomware is set up in JSON, and what they tell it what to do. This has been created by someone for a third party to use it. So that's it. They give you a kit, and then you said, okay, so today you will be attacking this version that we will be launching to the street to steal things from people. However, this will only be used in some countries. Some countries are excluded. I believe that this campaign did not affect Russia or Ukraine. They take they see if you are in those countries. If you're in those countries, they do not attack you. And if you have ABEL solutions in place, they stop the campaign and then or move on somewhere else. So they have the option to disable antivirus functions. They also have options to detect whether they are in VirtualBox or any other virtual environment. And then the person receives it and says, oh, I don't want you to attack my country, so therefore you will not be carrying out any attacks in Russia because I work for a mafia, so we are not going to attack each other. And that's the way it goes. So these are criminals and mafia trying to make money. Well, and I guess that there are also these naive users who buy these kits, but these ones soon end up in jail. So as I say, I was told that DLLs had been modified, but that didn't make any sense to me, having modified DNLs in ransom, because that's not the way they actually do it. So my question was the following: are they acting as a file infector? Are they propagating themselves? Are they affecting other files in the system? So this doesn't really make sense. So that's why I decided to carry out the analysis. So therefore, I decided to to work with the server code. Oh, we are doing very bad with time. Only 15 minutes left. So server has several deciphering or decryption chain. You know, we can have chains in WHR, multibyte, when we see characters 0, 0, and multibytes are just the ordinary ones, PP, you name it. So here we can see a function. It will encrypt WHR chains, and here we see a number of parameters. This is the offset, where in the file we have the chain text, the text string encrypted. So this is the size of it, 12 bytes. And then the key to encrypt that string. I did an analysis of this to see what each of these functions did, the previous one and this one. So these functions check pointers. They also check that the address that they insert in the stack is pointing at an area that can be read, that there is good enough memory to write on, that the function is not altered by other execution threads requesting or calling on that function. So at the end, an RC4 takes place. And now that I know that, I take the strings and I start to encrypt them, to decrypt them, to analyze the binary. So locating these decrypting routines is not done randomly. We have tools within Radare that tell us where to find those functions. We know that programs use lots and lots of strings to call, register, to resolve APIs, to show you messages. There is lots and lots of text in a program that is to be parsed. In this case, they have just eliminated it so that to make our analysis more difficult. But logically, if there is lots of text, the function to decrypt that function, that text, is called several times. And here we see all the calls that have made to those functions. What is the logic that we follow? Well, we just look for the most frequent calls, 137, 100, and these are the offsets that are functions that I showed you before. This command is enough to rule out, to leave out many of the functions that are not linked to decryption. We may have false positives because what some functions are called frequently, for instance, copy memory or host memory. But in this case, we clearly see that these are the two functions that we want to locate. So there is a problem to this command. It is not represented in JSON, so therefore it is more difficult for us to use it in NetScript. However, we can create a script that will tell us about the most frequently called functions in the program and to show those functions to us. Doing a script of this kind requires those three commands. R2pipe. As I told you before, R2pipe, that's an input. R2pipe CMD, R2pipe CJ. And this is as much as you need to do. To know. Well, we only need to know what the AAA command does. We said that before. Analyzes the binary. What does FLJ does, and XJG. The last one gives us the references of the calls to the function that we select. This is not very large, only long, only 19 lines. R2pipe file is imported, JSON, and here we have this fixed JSON function, and this is so because when in Windows I asked it for a JSON data, My string comes with a number of characters to delete the colors of the console, etc. And in that case, I cannot parse it. And as you can see in this version, the only thing that this version does is just to cut the string here, where we have this -r -n. And this only happens in the Radare version for Windows. So you have to bear this in mind. Therefore, so this is how the file is opened. We start by the command line. We ask it to analyze it. We ask it to load it within this J variable, so all the functions of the programs, and then we iterate according to the JSONs that we have found, and we want to find the offset of that function. When we have the offset of that function, we use the axdj command. We give the offset to it so that it gives us back all the calls that have been made to that function. And last, I insert it in a dictionary using this lambda. Don't ask me what this is for. I just found this one and I said I wanted to order them. Okay, I don't know very much about Python. And last, I just go through that list, which is already in order, and I ask it to show me the first top results of that list. And when I run it, this is the result. Well, sorry to show you all these demos. These demos are recorded, but I cannot really show them live because I just don't have the time for it. So this is the same script. We have created it, and now it will execute. It will be executed, and here it will tell us about the functions and the calls made to those functions. These are the top 4 of functions, and these could be the possible decoder functions. Let us see what else we can do with Radare2 scripting and how they can help us in our analysis. Well, we know how to get the functions and the calls. However, we just have numbers. We cannot really check whether this is correct or not. It would be very good to show the code that is calling each of these functions, as well as to obtain some code to see what happens behind. Because I ask you that it always enters a k value, a length, and an offset. If we see that pattern, we clearly see that this is the function that we are looking for. It would be good to get the encrypted chain, the key, and to decrypt it, and it would be wonderful to fish the binary so that we can see what was behind those text strings. Showing more information. This is as simple as adding these 4 lines of code. What are we doing here? This is the result of the top 4 functions. And now I will go to that function. I will go 4 instructions back, and I will disassemble 5 instructions. I just want to have a snapshot of the parameters that are sent out to the function that I'm calling. After that, we have to get the encrypted text screen, the length, and to decrypt it. So here, this is the function that we are calling. We have obtained this function through references, and we know that we take it from here. We go to the offset of that function, and the only thing that I have to do is to go back and to find push functions, because push functions push only values. So therefore, we can look for the disassembly to go back, and then through the commands that we have here, SSO, AOJ, and PA, we said, okay, I'm here. I ask it to go back an instruction. Then I check that that is a push that inputs a value on the stack. And if it's so, well, it has met my requirements, and I store that value, and that will be the offset of the calculates what the value or what the chain is. So I go back one instruction. Is that a push? No, it is not. Then I go one more instruction back. If it is a push, I just get it. So the algorithm is very simple to implement. The I'm not going to show you the script because it is a bit long. And once we have all the information, we have all the functions, all the calls, all the parameters, and all the decryption keys, we are going to put it in a table. We are going to parse it, and we are going to say, go to the offset that we have gotten from the table that we have created, where I store the screen, then give me the value of it and the size of it, and then I ask it to go to that position. Position is value. Go to the chain. Chain is equals the code, the data that I got, and then I ask it to write that string in that position. And that's the way we fish the file. I copy the file and server.py. Bear in mind that we are not running anything. I just found out that it was an IC4 and I'm just doing binary analysis and obtaining information. I have created a program, I'm sending out parameters to it, it's Python, and then it gives me an output, and I say these are the possible functions. Based on -e parameter and one of the functions I found, I can verify whether the function is the one that I'm looking for or not. This goes right away to e parameter, and then I ask it to go here. These are the strings that have decrypted. This is typical of malware. So scripts has fulfilled this function, and now we have all the encrypt strings, and now it has fished those strings, and now I'm going to ask it to show me the list, and I'm going to take the second function. Then I ask it to use this encoder function. And it will do exactly the same thing. It will show us all the decrypted text strings. So that's very interesting, because if you create a file, then it enters, it includes its decrypt statistics. And last, well, I wanted to show you the text string within Radare, but this is too small a screen. You will not be able to see it, so therefore I will move right away to the next clip, where we can use, where you will see many of the UIs that we have for Radare. This one is being worked on by a colleague, Alberto. It's created in .pnet. And then with all that, he just created a full UI. First of all, I will upload the binary file without any, that has not been altered. I'm sure that I are used to the other views. Okay. So this is the function introducing the size, the call. We are going to take a look at the text reference that was found after the analysis. So this is in Chinese, just don't understand. And let us try to find some text strings. So notice that the only thing that we have is a broken file here. I don't know how long it takes to open the next file. So here, no strings. I will upload the file that we created with our fish tool in Python. And we should be getting the text strings so that we can carry out a deeper analysis of our binary. So we go back to the text strings. So notice we see all the strings looking for extensions to be encrypted, CND, auto delete. So from here, analyzing the binary is very easy because we can go right away to the code. And here, if we take a look at the string, it tells us what happens with that encrypted string. And this is the file root. So this is quite easy. With 10 Radare commands, we have a tool that speeds up our analysis. This tool is generic for any server family because, as I told you before, the code, they don't change it. They have used the same code in 5 different campaigns. Have I finished? Yeah, no time left. Okay. Therefore, I have to finish. I have more information to share with you. Well, okay, 5 extra minutes. Thank you. As I said before, now we can analyze the binary file. We can take a look at the text strings. And when I do my reanalysis on those text strings, and when I see what I do, the else were being parched because it is a way used by server to elevate privileges in the system. And this is about copying a file that they know have elevation privileges. They go to file 32, they take a look at the manifest of that file, and then they check whether the file can be elevated in Windows, have elevation options. And if this is the case, they choose DLL. I was about to say they choose it randomly, but they do not choose it randomly. They choose it based on number of parameters. They copy that file in a temporary directory, as well as the DLL. They modify, they change the DLL so that when the file is running that file, the DLL of that file will be open, but not the one in system 32. They will modify the code that they have entered so that server is run, and in this case it is elevated and it has full access to the system to infect it and to destroy it if that was the case. So mystery resolved through our tool, and now I'm in a position to say to my colleagues at work that we are doing this, I'm doing that for that reason, and that tool is ready to use by someone who is not an actual researcher or an analyst. Now, payload. Payload, it is very frequent that your machine receives an exploit kits that you receive when you visit a number of sites. Well, there are some legit sites that have been crashed down by someone, and they have those exploit kits. And then out of the sudden, when you go to those sites, you are just infected. In those cases, as I say, they take advantage of Flash, and they introduce a payload that is executed in the memory. Often they are ciphers with a small routine trying to hide the behavior. Radare2 can help us decipher this type of payloads. So payload, neutrino, you visit the site. If it is vulnerable, they use the hacking team payload. And payload has a small layer of encryption. This is the hexadecimal. Those of you who are used to reversing, you will see a jump of 12 instructions up there. This is the code. This is a jump to line 14. And from here, it will do all the code. So what is the code doing? Well, these codes make sense up until here, up until call to. Once the call is done, it goes into position 2, and this is a decryption loop. This is a payload, it is in the memory. You have to see, okay, you're doing short with 64, have to calculate the value of AC, of CX. So Radare.
This is an internal virtual machine which can emulate any instruction from any processor, from any architecture, okay? This I will not explain because we don't have the time. I'll just show you how we decode the payload with two commands, just two commands from Radare. So we load it in read mode, we disassemble, we see the code. Once we have disassembled, I start the virtual machine. There will be values so that we can work. It executes the instruction and shows 10 lines of disassembly. We have gone all the way through here. It executes the instruction. It's executing code. Okay, so it's getting values. We have values there. As if this was being executed in a controlled environment. This will never execute in your real computer. I will tell it to execute this until after line 14, which is where you have this. Okay, so executing until line 12. It finishes the loop, and if we show the code, take a look underneath. We have decoded the payload. It will look using the APIs, do a CMD exe, and then do all of this. It will download Kerber and go for the ransomware. I had a few things to tell you, but Roman is looking at me because I've run out of time. I hope we have demystified Radare a little bit, because, well, people talk about a very steep learning curve. I've never seen such a steep learning curve myself. I'm very clumsy for these commands. I can assure you, if I try to do what Pancake does, no way. But then you go around your basic commands and you check help, and anyone in this room could do this, and more than this. So I would encourage you to play around with Radare. Don't be scared to use it. You can use very exotic architectures, okay? Not just x86. That's it. I have to stop there because I don't have any more time. Thank you. I'm not trying to apply censorship to what you're saying. Questions? Remember to stand up because we cannot see you. You're so overwhelmed that no one dares raising a hand. Well, it seems very easy to me. No, honestly, it's a question of getting your hands on it. Yes, I've been working on this project for 2 years. In the first Root.com conference I attended, no idea about Radare. Then I started doing things. In some channels, I even said that Radare was a useless tool, that it didn't make any sense. I'm so sorry I said that. I regret that so much. Pancake will kill me. Pancake is asking, should we do streaming on that? Well, look, he knows. I told him. It was a conversation in our Telegram channel. But my life changed completely when I started working on it seriously. Well, first of all, I would like to congratulate you. The question I have is, just as you saw the functions that I called statically, can you do it dynamically? Can you execute and see the stack working? Well, the original script did it dynamically. At first, when I started doing this, I didn't analyze the decoding routines, so I did the same script, but using debugging commands. That's why I showed you the debugging commands. I did the same search, and then I told it, okay, I'm going to save the offsets where I found the push. So go to this offset, debug the step. I will execute that offset. I will go for push. Next offset, push inside, DSO in the next offset. I would execute cow in real time and I would decode the entire string. No problem doing that in that way. With Radare and scripting, you can do whatever you need. In this case, I went beyond that. I said, well, if you take a strange binary, I mean, this is getting executed. If you don't do it in your virtual machine, you can have problems. You can do any tests using a virtual machine. Quite easy. One last question. Congratulations. I think this is one of the talks about Radare that I found more clear. I mean, compared with Pancake, completely different. With the ESIL, can you execute binaries that are made for other architectures? Yes. I did have a demo that I wanted to show you. Did you see my talk last year? I talked about a rootkit. We did an emulation at that time. I have a script that emulates the bootloader for the system with ESIL. We can decode the initial code for Romneys. So you can execute that code in memory. You can decode the original VBR to restore it. That was a demo that I had in place, but I ran out of time. I wanted to show you today. In the previous conference, I did have a workshop on this, but if you're interested, in the GitHub for Radare, you can access information about R2Con. There you will see all the workshops and a demonstration of this with malware from last year. That is the basis for everything we did. 16 bytes, by the way, 16 bits. With data segment, no problem. You can use it without tweaking. Thank you very much, Abel. Thank you. I hope you didn't get too bored.